Like many of you, I grew up in a rural area. And being a country boy, you have to learn how to do a lot of things for yourself, such as change your own oil or even put on a new set of tires. One thing I learned very quickly was how to use a cheater bar to gain leverage when you're using a socket or a wrench. Now at the time, I didn't understand all of the physics behind what I was doing. I really didn't care as long as it worked. However, things have changed a little since then. In addition to the types of motion that we have witnessed in the previous labs, straight line motion and projectile motion, objects can also spin around an axis. We call this type of movement rotational motion. Since it is a little more difficult to measure the speed, like in meters per second, of something that is spinning around an axis, it is sometimes easier to measure it in terms of how many times it makes a complete spin, such as in revolutions per second, or revolutions per minute, like it is for your piston cycles on your car, or revolutions per hour. If you've ever used a wrench to try and loosen a stuck bolt, you probably realized very quickly that where on the handle you grabbed the wrench was very important. The farther down the handle, in other words, the farther away from the bolt that you grab, the easier it is to break the bolt loose. Naturally, the direction that you push or pull is also very important. If you push up, for example, you will only tighten the bolt even further and, assuming it is already as tight as it can be, produce no rotational motion. All of these factors affect what we call torque, which is defined as the tendency of a force to produce a rotation. The equation used to calculate torque is listed here, where tau represents torque, F represents the applied force, and R represents the distance along the lever from the center of rotation. As you can see from the equation, when all other variables are equal, a force that is applied farther away from the center of rotation will result in a greater torque. Realize also that if the force is applied at a right angle to the lever, or at 90 degrees, as opposed to some other angle, you will obtain a greater torque since there will be a greater downward force. The units for torque are generally Newton meters. But in the English system, it is often measured in foot-pounds. Realize too that equal torque applied in opposite directions cancel each other out. And as a result, no rotation occurs. The only way to get rotation to occur is if the net total torque on the system is greater than 0. In this experiment, you'll be using the setup shown here to try and keep an object that is not rotating from rotating. In other words, you will try to balance out the torque on both sides of the meter stick. You will create your lever by delicately balancing a meter stick from near its center while it is hanging from another meter stick by a loop of string. When the string is located in the position that will achieve balance, record the balance point, which will be called X sub 0 in your lab procedure. Then tape the string to the meter stick at that point. You will then hang various masses by a loop of string on either side of the center of the meter stick according to the laboratory procedure in an attempt to balance the rotation. Since you don't have calibrated weights, you can use quarters instead. Just tape them together according to the specifications listed in the laboratory procedure. Once you achieve balance, which is called static or rotational equilibrium, calculate your torque values using the weight or force and the distance from the center for both sides of the meter stick. In other words, both lever arms. Be sure to record your data in the proper data tables. So now hopefully you can understand why a cheater bar works. It allows you to apply a force that is farther away from the center of rotation, resulting in a greater torque and thus a greater rotational motion.